Welcome back to the channel. Centrifugal pump, working principle, and curves. This simple yet powerful device is crucial for everything from bilge pumping to main engine cooling. At its heart, the centrifugal pump operates on a fundamental principle, converting rotational kinetic energy into the hydrodynamic energy of fluid flow. Think of it like a slinger, throwing water outwards. The main components are the impeller and the casing, often called the volute. The impeller, mounted on a rotating shaft, has a series of curved vanes. As an electric motor or turbine drives the shaft, the impeller spins rapidly. This rotational motion imparts high velocity to the fluid between the vanes, accelerating it radially outwards due to centrifugal force. The fluid leaves the impeller tips at high speed. Now, this high-velocity, low-pressure fluid needs to become high-pressure, usable fluid. This is where the volute casing comes in. The casing is a spirally shaped passage that progressively increases in cross-sectional area as it wraps around the impeller. This gradual increase causes the fluid's velocity to decrease significantly, which by Bernoulli's principle leads to a substantial increase in static pressure. The pressurized fluid is then directed out of the pump's discharge port. The rapid exit of fluid from the center of the impeller creates a low-pressure zone or a partial vacuum at the impeller eye, which is the suction inlet. The higher atmospheric or static pressure on the surface of the fluid in the suction tank then pushes fluid into this low-pressure area, ensuring a continuous flow into the pump. This continuous process of creating low pressure and converting velocity to high pressure is the essence of its working. In a marine context, these pumps encounter varying operational demands. To understand a pump's suitability, we use pump performance curves. The primary curve is the head capacity HQ curve, which plots the total pressure head the pump can generate against the flow rate capacity. Head is essentially the height to which the pump can lift the fluid. Typically, as the capacity flow rate increases, the head generated by the pump decreases. This inverse relationship is characteristic of a centrifugal pump. A steep HQ curve means a small change in head results in a large change in flow, while a flat curve means the flow is less sensitive to head changes. Another critical curve is the efficiency capacity curve. This shows the ratio of the power delivered to the fluid versus the power supplied to the pump shaft. Pump efficiency varies with the flow rate, peaking at the best efficiency point, BEP. Operating near the BEP is vital for minimizing energy consumption and wear on the pump. If you found this video helpful, please give us a thumbs up, hit the notification bell, comment, like, share, and subscribe for more insights. Thank you.